Hello again, my name is Brandon. It's been a second. I'm a licensed engineer who's just designing a diesel engine for no good reason. Where we left off last time is a representation of a basic cylinder, basic crank, basic rod, the beginnings of a camshaft, the beginnings of some valves. And I've been away for a while because last time I did a video, I basically said you need to step back and see if we can start doing some math to actually start refining this into reality. And so what I did was I used the book I mentioned last time, which is the Diesel Engine Reference Book. And in that book, there is a chapter on simulating um, the diesel engine cycle. And it was not easy to do. I'll tell you that much. But I'll give you, and I'm not going to attempt to uh, explain how to write code, to write simulations, or do the math behind this. If that's something that really interests you, I can dive into it deeper. But chances are maybe the 1,000-meter view from above is enough. So the book basically centers this entire simulation methodology around this equation. And for those who maybe aren't so great in differential equations, I'll briefly explain what it is. And if it's not fully understood, that's okay. Really, the end result is just what I wanted to show. This equation is this side of the equation on the left side of the equal sign is simply the change in internal energy inside of a cylinder, a control volume, or an engine cylinder, per unit of time. So change in energy per unit of time. Yeah, but this doesn't look like that, right? It's got all these weird terms and DUs and DTs. What does all that mean? Well, very quickly, M is mass, so mass in the cylinder at any instant of time, the mass of the air or the mass of the gas at any instant of time. Du dt is the change in internal energy within that cylinder per change in temperature. So this is mass, change in energy per change in temperature. And this T dot is change in temperature over change in time. This could have been written du over d little t, but I think the author thought it was too confusing to have little t's and big T's, so he put T dot to say dt dt, so d temperature per unit of time. So mass times the change in internal energy per unit of temperature times the change in temperature per unit of time plus mass again, change in internal energy of the cylinder per change in phi. I'll talk about what phi is in just a second. And then this is change in phi over change in time plus internal energy at an instant, the current internal energy, not the changing internal energy like these are, the current internal energy times change in mass in the cylinder over change in time. All of that equals to, this term represents the inlet port and the exhaust port in the diesel engine. So equals the sum of the product of the inflows of mass times that inflow's enthalpy and the exhaust outflows times that exhaust gas's enthalpy minus the loss of heat through the walls of the cylinder minus P V dot. And V dot is change in volume over time. This term is the work done by the piston. If you are a mechanical engineering major, you probably know what all this means. If you're not, just throw it out. You don't need it. I'm going to show you what it ends up looking like. So this is some code I wrote in Python. And what this does is it solves that equation I just showed you at one tiny instant in time, and then advances the time forward a tiny little bit, and then does it again, and then advances the time forward a little bit and does it again. That's how things like video games simulate gravity and objects bouncing on each other and moving, is this same method. So basically my estimated bore is 80 millimeters, so that's 0.08 meters. Stroke, I just threw in 0.085. The length of the rod, 100 millimeters or 0.1 meters. And then don't worry about all the rest of this. So the first thing I'm going to show you is I'm going to run this, and this is going to simulate this single cylinder engine operating at 500 RPM. And right now, this little hash mark means comment, which means this is ignored. Right now, this MFT is how much fuel I'm injecting per cycle in kilograms, and I'm putting it at 0. So I'm going to run this simulation as if there's no fuel being injected. It's just spinning free at 500 RPM. Imagine like something hooked up to it, forcing it to spin at 500 RPM. And we'll see what kind of things develop inside of the cylinder. All right, there it goes. Boom. Okay, so what are we looking at here? This is the big one. This is temperature over time. So I ran this for 1.5 seconds, which gives you at 500 RPM 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 12 and a half or 13 revolutions of the engine. And if you imagine the cylinder just pumping in and out, in and out, in and out, compressing the air, but there's no fuel to squirt in once it's compressed, so it's just going back to it just kind of gets high pressure and then is relieved and the piston is allowed to move and then go back to low pressure and over again. So let's talk about phi, that term over here that I was telling you about. This guy here, phi. Phi is the equivalence ratio, which means if you take the amount of fuel divided by the amount of air, and then divide that by the perfect fuel to air ratio, that's what phi is. So it's like your fuel to air ratio divided by a perfect stoichiometric fuel to air ratio. And I'm not injecting any fuel, so that ratio is 0. It stays 0 the whole time, which is correct. The volume, this is simply the cylinder pumping, so inflating the cylinder and deflating the cylinder, inflating the cylinder, deflating the cylinder, back and forth and back and forth. Because there's no fuel, and this is just dependent on the speed that the engine's running, this looks like a perfect sine wave all the way through, which is correct. And I've checked this math on this part of the graph, and it checks out from separate, verification. So these three are still could be wrong. There's a lot of math hidden behind this that is going to take a long time to double check. At first glance, it seems to be pretty okay. Some of these numbers do check out if you just estimate, if you compress a gas 22.5 times, if a 22.5 to 1, let's say, compression ratio, what temperature would that be? Yeah, you end up right around here in the 900s, 1,000 Kelvin range. So this is kind of checking out. So this is every compression, the temperature in the cylinder goes up to about 929 Kelvin, and I'll tell you what that is in Fahrenheit. So 929 K to F. So that's about 1,200 degrees. Not sure yet, but we'll see. Down here, this is just the mass of air in the cylinder over time. As the zero time mark, the beginning, we start at top dead center, starting to suck in, starting to draw in air from the intake port. So the cylinder fills up, so the mass of the air in the cylinder increases. But once the intake valve closes and the compression stroke starts, the gas is compressing, but no gas is leaving or entering the cylinder, so the mass stays the same. And then when you open up that exhaust port, so this is intake, compression, and then expansion. Fuel injection would be right in between here. You'd normally inject fuel right here. The reason this spikes up is because I haven't messed with the valve timing yet. So when I'm opening the exhaust port, basically there's a vacuum in the cylinder at that moment and air is flooding in when I open the exhaust port. So it's like the exhaust port is operating in reverse, which is why you have this spike here, which has to be massaged out. I'll have to make adjustments to everything to make this maybe not do this. So this kind of checks out. This kind of stands to reason that this probably is okay or close to okay. And then down here is the pressure inside the cylinder. So this is the cylinder compressing. This is where fuel would be injected at the point of highest pressure and highest temperature. and then it goes back down again, and then another compression cycle, and back down again. And these small spikes is because the exhaust valve isn't big enough. So as you're doing your exhaust, this engine, I'm locking it in, forcing it to spin at 500 RPM. As the air is trying to force its way out, the valve is restricting it a bit, so you're having a buildup in pressure during the exhaust stroke. Okay, so that's just the engine free spinning. So let's add some fuel. Rerun this with this tiny little bit of fuel squirted in. All right. Now we're cooking with peanut oil. All right, so look at this now. So now temperature is up, pressure is way up, and this is your fuel equivalence ratio. So this is how much fuel to air we have, which is a little over this is 0.48-ish compared to stoichiometric. And diesel engines run lean. You're never at 1. You're always below 1. You're somewhere in the range of 0.2 to 0.8 or something like that. When you start getting close to stoichiometric, that's when you start getting the black soot and everything out the exhaust pipe. So this is jiving. I mean, you're injecting fuel and bringing your fuel to air ratio up and then back down again during the exhaust stroke. This has stayed the same. All of these graphs on the left are still suspect, but it looks good for now. So with that, I'm gonna end it. I just wanted to show you, this is, I guess, a kind of a nerdy thing. I mean, I've spent a lot of probably time on this that maybe was for nothing, but you get sucked into projects like this and you just want to share it with someone. So here it is. I'll see you next time.